Hi everyone, my name is Sab, and tonight we will be discussing about decision trees. So, decision trees is a machine learning algorithm under information based learning. So, when we hear about information based learning, we have to keep in mind the saying that information is the resolution of uncertainty. So, this is a supervised machine learning algorithm. When we say supervised, we feed information for descriptive and uh, for descriptive variables and the target variable. So we cannot talk about information-based learning without tackling about decision trees, because decision trees is the fundamental structure used in information-based learning in machine learning. So we will also be talking about uh, entropy and information gain. So, information gain. So, in this video, we will learn how to solve for entropy and information gain that we will eventually use in creating our decision trees. So, what you can expect in this video is that I'll explain these two and provide a real world example and manually solve for them in a smaller sample size. So decision trees is composed of um, root node. Let me just write it here. It's composed of root nodes, one root node, and then interior node, and leaf nodes. So root node is also known as the starting node. And in our decision tree that we will be creating, the shape of the root node is in oval or oblong or even circle. Interior node or interior nodes is what comes underneath the root node. So there could be multiple root of interior nodes. So it could be plural. And the shape for this is also in circle or oblong. In leaf nodes, these are also known as terminating nodes. And these terminating nodes are in the shape of squares or rectangles. So these, with the word terminating, it means that this is our decision if we come with this side of the tree, or this one, or this one. So this is the end node or the leaf nodes. So the root node and interior nodes specifies a task to be carried out on a descriptive feature. So this produces options. These two, root node and interior nodes, they produces questions and with answers. So the number of possible levels that a descriptive feature can take determines the number of downward branches from a non-leaf node. So each of the leaf nodes specifies a predicted level of the target feature. So that's why we have the leaf nodes here, because they are the end nodes. So we have a question that should be asked: how do we decide which is the best decision tree? So which one is really the best decision tree? we have a rule of thumb in machine learning. So the shallower the tree, the better. So use fewer tests or interior nodes. So when we're comparing decision trees, we would like to see decision trees with fewer interior nodes. And the shallower the tree, the better. The better. And we need to put the descriptive features that best discriminates between instances that have different targeted feature values to the top of the tree. Entropy earlier, and to measure the discriminatory power of descriptive features by analyzing the size and probability of each set of instances created when we test the value of the features and how pure each set of instances is with respect to the target feature values of instances it contains. So that's why we need to solve for the Shannon's entropy model. So just in case you're not familiar with what I've just mentioned, descriptive variables and target variable. So this in statistics are more like the axis, and in statistics this is more like the y. We have this descriptive features and we have the target feature. So what entropy model does is solve for how pure it is. So how pure it is or how impure it is. So basically it is a measure of, let's just say, impurity of the elements in a set. So if we go back to the rough decision tree I've created, so this would be a set of elements, right? If they fall in the criteria that belongs here, this is another set. And if they belong here, this is another set of data or instances. We call data points in machine learning as instances. And this is another set if they fall within this interior node. So essentially, it measures the entropy, or Shannon's entropy, measures the heterogeneity of a set. So the mathematical equation for the Shannon's entropy model is h of t equal to, I'll just use different color. I think I should use a different color. So the mathematical computation or equation is h of t is equal to the negative of the summation of I equals 1 to L, probability of t is equal to I times log base 2 of p of probability t equals to I again. So remember these formula because we will be using this in every decision tree that we will be creating. So the probability of t is equal to I here refers to the probability, let's just say PRB, or probability that the outcome of randomly selecting an element, let's say I. L here is the number of different type of things in the set. So I'll just write it here, the number of different types of things in a set and the 2 here is actually the arbitrary logarithmic base. So we will be using 2 here all the time. So the minus sign here is added because we have a logarithmic right here, that which makes the possibility of having a negative value. So we need to have a positive value so that we have a negative sign right here. So for example, consider our set of 52 different playing cards and the probability of randomly selecting any specific card, let's say I. Probability of selecting a random card, let's say I, is equal to not equal to, but I'll use 1 over 52. So you have 52 unique cards and the probability of selecting a unique card is 1 over 52 and we don't know the card yet. So we could solve for the entropy by using Shannon's model of entropy, which is H card is equal to negative summation of I equals 1 over 52. The probability of P card is equal to I times log base 2 of probability of card is equal to I. So this is summation 152 and this is 1 over 52 times log base 2 of 1 over 52. So you may use your calculator and you would get 0.019 times negative of 5.718. So therefore we have negative of summation of I equals 1 to 52 and then negative 0.109. So that is 5 6 6 8 bits.